Okay, here we have a spherical mirror problem. In this case, we have a mirror that is polished on both sides, so it can be used as either a convex mirror or a concave mirror. And what we're told here is when we use it as a convex mirror, we have a magnification of positive 1/4. All right, so for some object. The question asks, what is the magnification when used as a concave mirror, the object remaining the same distance from the mirror? So I like to imagine this one as like some object in front of the convex mirror, and then we just like spin the mirror around, and now it's a concave mirror, but the object hasn't moved and the mirror hasn't moved as far as their locations. So, kind of cool things to think about, things you can relate in this problem. We want to start off, of course, with the mirror equation, which I'm going to write in terms of the object distance and image distance. 1 over f is equal to 1 over p plus 1 over q. And image distance and object distance are written in different notation, different places. Sometimes they're, DO, DI, but in order to not carry around the subscripts, I'm using a classic notation of p's and q's here. Okay, so what I like to do when I'm using this equation is solve it in equation form, solve the general equation for the thing I'm looking for. That's always the more elegant approach. But especially in the case of a problem like this where you have fractions, is to solve for your unknown first and then sub in whatever it is that you need to sub in. So for instance, if I take this equation and I solve it for q in general, what I get here is pf divided by p minus f. Okay, so that can be useful. Now I'm going to start here by focusing on the convex mirror here. What I know about the convex mirror is, and you know too, that the focal length is negative for a convex mirror, right? So I'll remind us of that. It has a negative focal length. Super important to be aware of all the characteristics of these optical components. So the two components it's the same one here because it's polished on both sides, but essentially component convex mirror and concave mirror are components with different behaviors. So this is negative focal length. So when I solve for Q for a convex mirror, then I've got to take that into consideration for this case. So I'll have there P times negative F, right, when I sub into the general equation. P minus, again, this is a negative F, negative focal length. And that gives me negative P F over P plus F here. All right, so that gives me that lets me know what my image distance is, right? And you might be like, well, why do I care about that? Well, I care about that because for this case, remember that I'm given that when we use it in a convex, as a convex mirror, that the magnification is equal to 1/4. So we're given this relationship, positive 1/4. That's super useful because magnification, the magnification equation is negative Q over P. So I'm going to actually put that over here on the right where I have these other equations here. The magnification equation, magnification is equal to negative Q over P. And sometimes students ask me about this equation and they'll say, well, does this mean magnification is always negative? Well, no, because that would mean the image is always inverted, which is obviously not the case. This negative sign, though, is in the equation. So Q and P can be either positive or negative, as you know. So you need to substitute the Q and P in with their appropriate signs when you use this equation. And remember that negative sign exists inside the equation. So as I would apply that for the convex case here, I would apply it that the magnification, the positive 1/4 equals negative Q over P. So if I set that up, 1/4 equals, now this is negative Q, right? So this equation here that I have for Q, I'm now going to put a negative sign in front of that. I'll do it explicitly just to make that hopefully a little bit more clear. PF over P plus F. And that's all over P, and I'm just going to say times 1 over P, just like that. Okay, so that reduces 1/4 is equal to F over P plus F. Little algebra there gives me that P is equal to 3F. This is really useful, right? This is now getting into what the object distance is. And one of the things we're told in this problem is that the object distance remains the same when we flip the mirror over. Yeah, so I care about this P equals 3F. That is useful. So now let's go ahead and switch gears and talk about the concave case. So these are our equations here. So let's talk about the concave case. So for the concave case, now my focal length is positive, right, for this case. Magnification, well, for positive focal lengths, let me go back a little bit. I can solve for the image distance for the concave mirror, and that will just be equal to PF over P minus F, right? Because my focal length is positive in the case of a concave mirror. So when I look at magnification now, because remember, that's what I'm after. They want to know magnification. I'm going to call this M prime since I'm talking about the concave case, equals negative Q prime, which would be image distance for the concave case, over P. Now P is the same for both cases, so I don't need to prime that one. So let's fill this in. M prime is going to be then, so negative Q prime would be negative PF over P minus F. So just, let me pause for just a moment. If you're wondering, like, why am I using the same F? Remember that this is the same mirror. It has the same curvature, let me say. The mirror has the same curvature. So if it has the same radius of curvature, then the focal length, even though they're going to differ by a sign between the convex and concave cases, they're going to have the same magnitude. So that's why I'm using the same F there. This is again times 1 over P. This allows me to solve for M prime, negative F over P minus F. And then I can substitute in my previous equations here to solve for M prime, the magnification I need. Because remember what I resulted in here, P equals 3F. So now all of a sudden that becomes super useful. Negative F over, now let me sub in 3F minus F. And this will give me negative F over 2F, which gives me negative 1/2. All right, so when I calculate a magnification, I expect to get a dimensionless value, first of all, right? It's just a ratio. So we have that. And then you can think about, like, does this make sense for a concave mirror? Is this a possibility? That's always another good thing to kind of run through your mind. So this would be something that would be diminished, right? Sure, that makes sense for a concave mirror, and inverted. Sure. Okay, so that's our answer for this one. Spherical mirrors are going to be these two types of spherical mirrors, convex and concave, are going to be two of the important components for you to learn about as we are doing geometric optics.